Today we'll be able to identify the sets of numbers that a given number belongs to. So what is a set? A set is a collection of things with the same characteristics or properties. An example of that would be silverware. Sets of silverware include knives, forks, spoons. Any of those are considered part of the set silverware. Or we could think about dishes. So what are dishes? Plates, bowls. So all of those are considered part of the set dishes. They have the same characteristics or properties. So for our numbers, we separate those into different groups with different characteristics. So starting down here with the natural numbers, the symbol for that is an N. And the natural numbers are our counting numbers, the ones we can count on our fingers, 1, 2, 3, so on and so forth. Moving up from that, we have our whole numbers, which is symbolized by the W. And the only difference between the whole numbers and the natural numbers is now we include 0. So notice that all of the natural numbers are included within that set. So natural numbers is really a subset of whole numbers. As we move up in this chain, we have integers. Integers now include our positive and negative whole numbers. So notice our whole numbers with 0, 1, and 2, so on and so forth, are included within the integers. Now we include our negative whole numbers as well, negative 1, negative 2, into negative infinity. Up from that, we have our rational numbers. So that is indicated by the Q. Rational numbers are any fraction or decimal that end or have a repeated pattern. That means 1/3 is considered a rational number. It is not an integer because it's not a whole number, but the integers, whole numbers, and natural numbers are still considered rational numbers. Negative 0.67. This decimal ends, so this is considered a rational number. The square root of 16, well, that can be simplified to just 4, and so that's considered a rational number. But 4 can be considered also an integer, whole number, and natural number. So a number can belong to more than one set, as we've seen here with the natural, whole, and integers. If a number doesn't belong to any of those sets, it could be considered irrational. These are decimals that never end and have no repeating pattern. We use the symbol I to represent this set of numbers. And these are numbers like pi. It's 3.1415926, all of those numbers, so on and so forth. And that decimal never repeats and never ends. It's the same for the square root of 2. The square root of 2 is not a perfect number. It is not a whole number or a natural number. It is a decimal that will never end. We can approximate it and round, but we'll never have the exact value that will be a decimal that stops. Same with the negative square root of 101. It can be negative, but this number cannot be expressed as a ratio or as a decimal that will repeat or end. If a number belongs to any of these sets, it's considered also a real number. And that's just all numbers. So all of these are considered real numbers. Now let's practice putting these numbers into sets. So we're going to name all of the sets which a number belongs to. So 30. 30 is a natural number. It would take a while, but we could count on our fingers all the way up to 30. If it's a natural number, we could say it's also a whole number, which makes it an integer, a rational, and a real number. So you want to try and find the lowest on our chart where it belongs, and then it belongs to every set above it. Negative 11 is part of the set of negative and positive whole numbers. So it is an integer, rational, and real. 5 and 4/7. Well, this is expressed as a ratio, even though it's a mixed number, which makes it a rational number and a real number. It is not an integer, natural, or whole number because it has that fractional piece with it. The square root of 21, if we were to put this in the calculator, we do not get a whole number. 21 is not a perfect square, so we can't take the exact square root of it. So this would be considered an irrational number, which means it doesn't belong to any of these other sets. It only belongs to irrational and real. 0 is a whole number, but not a natural number. So it belongs to the whole, integer, rational, and real number sets. The negative square root of 9. Well, this is negative, and the square root of 9 can be simplified. 9 is a perfect square, which gives us 3. So negative 3 is an integer, a rational, and real number. 6 over 3, or 6 divided by 3. This is a rational number, but it can be simplified. 6 divided by 3 is also 2. 2 is a natural number, whole number, integer, rational, and real. We saw pi as an example of an irrational and real number. This little line above the 3 in this decimal means that this 3 will be repeating. A repeating decimal is part of our rational number set. So this is rational and real. The square root of 144 can be simplified. So this is expressed as a ratio, and the square root of 144 can be simplified to a real number and a rational number. The square root of 144 is 12. So when we simplify this, we get 12 divided by negative 3, which is negative 4. Negative 4 is an integer, rational, and real. We have negative 2.875. So is this an integer? No, because we have that decimal portion here. It is not a negative whole number. So this is just part of our rational and real number sets. Number 12 looks a little weird, but it's the square root of 17 divided by the square root of 17. Just by itself, the square root of 17 would be considered an irrational number. But because we're dividing it by itself, this actually simplifies to be 1. 1 is part of our natural numbers, whole numbers, integers, rational, and real number sets. So even though the square root of 17 by itself would be considered irrational, because the entire expression simplifies to a natural number, the whole number is part of all of those sets. Alright, I'd like you to copy down this chart into your notes, and also each one of these numbers A through J. Your directions are to place the letter of each value in its location in the real number system below. So where that number would be placed, if we could place it into its group.